Hi, everyone. My name is Masoud
Hello.
Badiei, and I'm a postdoc at Stanford University. And the topic of this talk is an theory for kernel learning in generative and discriminative models of machine learning. And this is a joint work with my colleagues at Stanford. Machine learning nowadays has a lot of applications, and you have seen a lot of interesting and intriguing results from these deep neural networks and machine learning in a variety of applications. But the one that here at Stanford we are focused on is the application of these methods for medical imaging. So there are many tasks in medical imaging that can be automated using machine learning. I have three examples here. One is modality transformation. Here, for example, you have a CT image and you want to take this as an input image and you want to transform it to some other modality like MRI or something else. And this is very useful because for some patients, for example, we have CT images can be obtained, but MRI images is more expensive. Another task in medical imaging is segmentation, where we have some images and there are some interesting region in this image that we would like to highlight using these deep learning methods. And it turns out that deep learning is very powerful for these type of tasks. And the last application is registration, where you have two images of the same modality from two different patients, for example, and you want to transform the image from one patient to another image from another patient so that you get a standard image from both patients. And these are just a bunch of examples. So now I want to take a look at the theory of machine learning and how these amazing applications are possible. So a broad range of machine learning tasks is just basically is about learning a map between two domains. So here, I'm assuming I have a map between domain X and domain Y, and the goal is to learn this map. And to see how different machine learning systems are based in this idea, I will first talk about classification models. So in classification models, for example, you have a image, and this image can be represented as a matrix. And each pixel in this matrix takes a value. For example, if you assume a grayscale image, then each pixel has a value from 0 to 255. And so if you assume this image as an input of a deep learning model, and the output you can assume is a label. So here, for example, I have a picture of a cat and a dog, and the output of this deep neural network is, it should be 0 or 1, depending on which image is fed into the network. So as you can see here, I'm learning a map between a set of matrices and to a discrete set of 0 or 1. The same thing is also can be applied to generative models. So in generative models, what we like to do is we want to sample from a high dimensional distribution. So you have seen, probably all of you have seen the images of these celebrities. So all of these images are lying on a very high dimensional manifold of distribution. And we would like to sample from this high dimensional distribution. And the way to do it is that we first sample from a very low dimensional distribution, like Gaussian. Then we take this sample from Gaussian and apply a map to this sample so that we get a sample from that high dimensional distribution. So here, as you can see, I have a sample from this Gaussian and I apply a map HX, and I get a sample from this high dimensional distribution, which is an image. So as you can see, in both cases, we are trying to learn a map. So how do we do that? So there are some distinctions about the procedure that we use to learn this map. In the supervised models, we are given a bunch of examples from this map. So I know the input and output of this map on a bunch of instances. And I can use these samples to learn the map. In the unsupervised model, on the other hand, we don't have the paired input and output of this map. But what do we have is a bunch of examples from each domain. So So if you look at the picture on the left-hand side, this is an example of a supervised model where I have a big picture of shoes and I have the drawings of those shoes. So these are paired. So you can assume this as a supervised model. But on the right-hand side, I have a bunch of images from some scenes. And I would like to transform these to some painting style. But these paintings styles does not correspond to the scenes that I'm interested. So even though I have some samples from the domain X and domain Y, these are not paired with each other. This is an instance of unsupervised model. For the case of classification, typically people talk about unsupervised models when we don't have a class label for our features. But in general, unsupervised means that we have a bunch of examples from each domain that is not paired with each other. Now that we have these models, the question is, what is the mathematical idea about learning this map? So in the supervised models, what we do is we typically use those examples to minimize the loss function. So the mathematical formulation is that I have a bunch of instances, let's say n examples, and I optimize the loss function. And this optimization is over some function class. So I'm looking for a map or a function from this function class f, and I use a loss function to find this function from this function class. In the unsupervised models, we don't have those paired instances. So instead, what we can do is we can optimize the distribution of instances. So in the unsupervised model, we try to minimize some divergence between two empirical measures. So as you can see, the first empirical measure is defined over the instances from domain X, and the second empirical measure is defined over the instances of the output space. And the goal is to find a map that minimizes this divergence. Do you have any questions so far? Is there any questions? Okay. I want to talk a little bit about unsupervised models. There is a nice way to reformulate this unsupervised case also in terms of some optimization. So as you know, in mathematics, you can define a divergence between two distributions as an optimization over a function class. So here I have a divergence between two distributions P and Q, and I can write it down as a maximization over some function class where I apply these distributions to the function from this function class. Some examples are like total variation distance, Wasserstein distance, and maximum mean discrepancy. So in the total variation distance, for example, we apply the function class is all of those functions that are bounded. In the Wasserstein case, we consider those functions that are Lipschitz. And in the maximum mean discrepancy, which I will talk about it later, we consider those functions from some Hilbert space. So as you can see, all of the famous divergences, those well-known divergences can be written in this very general form, where you can change the function class and get different notion of divergences. So if I plug this definition into my unsupervised model, the objective unsupervised model, then I get a very nice formula, which is a min-max optimization. So in the supervised model, I have an optimization over one function class. In the unsupervised model, I have a min-max optimization over two different function classes. So the main question and the main topic of this talk is how can we choose these function classes? So typically when we want to solve these optimization problems, we apply some gradient descent or stochastic gradient descent to vector spaces. And now I'm talking about optimizing function from function spaces. So to do this optimization, we have to transform these optimization problems over some vectors. And that is exactly what people do when they apply deep neural networks. So the idea of deep neural network is that instead of searching over some function space, I can optimize over some vectors. And the parameters of this deep neural network can be used as a way to search over this function space. So deep neural network, I know most of you are familiar, so I just quickly go through this slide. So in deep neural network, you have many layers, and the parameters of these layers can be used to approximate a function, basically. And you have some nonlinearity that helps to do this approximation. So if we are dealing with nonlinear functions, we better have some nonlinearity. And typically these activation functions are ReLU, logistic, or arctangent. So if I go back to this supervised and unsupervised objective functions, and I replace this optimization over function class with optimization over deep neural network, this is what I will get. So as you can see now, I have some optimization over some bunch of vectors or matrices in this case. And this can be solved using various methods from optimization theory. And for those people who know more a little bit about this deep neural network, they can recognize the second optimization as a generative adversarial networks. So this min-max optimization is precisely what GANs is about. You have a minimization which is over discriminator, and you have a maximization over the parameters of, you have a minimization over parameters of the generator, and you have a maximization over a parameter of discriminator. And the idea is that if I feed a random noise to the generator, it produces some image, and the discriminator tries to discriminate whether this image is fake or it's real. So this min-max optimization is precisely GAN. Now, the question that comes here is it a good idea to replace these function classes with deep neural network? If you listen to most of the talks, they say, yeah, deep neural network is a great, fantastic idea. And most of the times they give a very good results. But there are also some cases where deep neural network actually fails to provide a good result. So I want to give you a specific example. For example, when we use deep neural network for training GANs, we have some issues about mode collapse. So this is an MNIST data set. The goal here is I want to produce digits from 0 to 9. And as you can see, if you train GANs, sometimes with deep neural network, sometimes you only get 1 digit out of GANs. And this is called mode collapse in GANs. And then the big picture is that using deep neural network makes these GANs more fragile to train. Any questions?
None so far.
Okay. So now, if we cannot use deep neural network, then is there any other alternative? The answer is yes. So kernel machines are historically were more popular before deep neural network became more widespread. So kernel machine is about, it has a more mathematical side into it. And this slide is trying to introduce the notion of kernels. So Hilbert is, I want to give you a bunch of mathematics from functional analysis, but I will go quickly. So we have a notion of Hilbert space, which is basically a vector space with inner product and some structure. And for each point from some domain, we can define a map from Hilbert space to real number. This map is basically takes a function from Hilbert space and evaluates the value of this function at point X. And if this operator is bounded, then we say that this Hilbert space is a reproducing kernel Hilbert space. Now, for each operator from this Hilbert space, there is a dual space. It defines a dual space. This duality is provided by this representation theorem. So as I mentioned, for each operator, you can get a dual form through this representation theorem. And this map here is called implicit feature map in machine learning. So you can assume that I can take any operator and I can represent it from using this feature map. And these feature maps belong to the Hilbert space. And if you take the inner product of these feature maps, you get precisely one object that is called kernel. So for now, you can assume kernel to be inner product of two elements of feature maps, where a feature map is basically a map from the vector space X to some Hilbert space. Why do we care about these kernel machines? The reason is that there is a very nice theorem that says if the kernel is symmetric and positive definite, then you can represent every function using these kernels. So a kernel is positive semi-definite if it satisfies this constraint over a bunch of points from X. And if you have, if the kernel satisfies this constraint, then you can take any function and have this representation of the function. So
excuse
basically,
me, Doctor. Yeah. We lost your voice for a moment there. Could you repeat what you said about the kernels?
Yes. This is a slide or
the
previous slide?
The next slide.
Yeah. So the idea of kernel is that if kernel satisfies some positive definite constraint, then I can take any function from the Hilbert space and represent and expand it in terms of the kernel. So you can assume this kernel as some sort of basis function that you can use to expand to get a representation of a function, right? So why this is useful? Because as you remember, we wanted to optimize some function over function spaces. If I have this representation of the function, I can optimize over the weights instead of optimizing over the functions. So this gives me an alternative for deep neural network where I can go back to this optimization that I had for supervised and unsupervised models. And this time I can replace them with kernels. So if I use the idea of kernel, I can write them using some vectors, and you have kernels here in the loss function. And these objects actually are quite well known in machine learning. So the first one is typically called kernel support vector machine. So if I use a very particular form of loss function, this is exactly kernel support vector machines. In the unsupervised models, this is something called generative moment matching network. So in this unsupervised models, I can actually make the loss function write it in a different form. So if I consider maximization over functions from this Hilbert space, then I get some notion of divergence between two empirical measures using kernels. So the bigger picture is that instead of optimizing the parameters of a deep neural network, we can optimize some parameters based on kernels. And now, the nice thing here is that by replacing the optimization over functions to optimization over parameters of this expansion, we can simplify the training. So it turns out that generative moment matching networks actually are much simpler to train. The same can be also said about kernel support vector machine. But they also have their own issues. The main issue here is that how do I choose the kernel? So I want to give you some specific examples of what happens if I choose a bad kernel function. So what I mean is that if I choose a bad kernel, it seems like I'm expanding my functions in a wrong basis, in terms of wrong basis. So as you can expect, if I choose a bad kernel, I cannot get a good result. And that's exactly what happens here in this case. So assume I want to do some segmentation here. So what we can do here is we generate some representation by applying a filter bank to the image. Then we select a bunch of a subset of these features, and then we apply our kernel, and then you use a support vector machine. So this last two step is precisely by optimizing this loss function. And here I'm showing the TSNE plot. So TSNE plot is basically a way of presenting high dimensional data in a 2D, right? And here I'm using a Gaussian kernel. And this Gaussian kernel has a parameter called bandwidth. And as you can see, if I choose a wrong bandwidth, then it's very difficult to discriminate the blue and red region. Here, the blue and red regions correspond to different pixels of this image here. So you can assume that the red pixels are those background region, and the blue are the one that we would like to segment, that specific region that we would like to segment. And if I choose a good parameter for the kernel, the discrimination is very easy. I can use a hyperplane to separate the red and blue region, and I get a very good segmentation results. But for bad choice of bandwidths, I get a very, very inaccurate classification result. The same is also true about unsupervised models. So if I choose a good kernel function, I can produce very high quality images from both MNIST and CIFAR10. But if I choose a wrong kernel, as you can see, I get some blurry images, both in cases of MNIST and CIFAR10. So this is a challenge, because if we want to use these alternative models, we have to select the kernel, and this is exactly the kernel selection problem. So the rest of this talk is about how can we select the kernel to get a good result from these models. So the idea is that both in supervised models and unsupervised models, I can go back to the loss function that I was trying to optimize, and I can add a maximization term, where the maximization is trying to maximize the kernel. So I want to try to minimize the loss, but I can add a maximization over the kernel. And of course, I need to know how can I do this optimization? What does it mean to optimize a kernel over some kernel class? So there is a very nice result by Rahimi and Rek. This is a classical paper in machine learning, which says that if you have a kernel which is shift invariant, it means that if I have a kernel evaluated at 2 points, it's equal to the value of kernel when you evaluate the kernel at the subtraction of these two vectors. So if the kernel is shift invariant, you can represent it in terms of an integral. These maps is called explicit feature maps. So as you remember, I talked about the object of a kernel as an inner product of two implicit feature map. The idea of Rahimi and Rek is that you can approximate this inner product with some inner product in L2 space. And this enables us to use this idea to do optimization over kernels. So before I move on, so as you can see here in this slide, I had some optimization over kernels. In this slide, what I said is that each kernel can be represented in terms of an integral, and this integral has a distribution. So if I know the distribution here in this integral, I can actually know what the form of the kernel looks like, because these feature maps are known. Here you have a bunch of random variables. So here, this distribution is the distribution of these random variables. So I can go back, and instead of optimizing over the kernel, I can optimize over some distribution. And I can replace the kernel with this expectation from the previous slide. Do you have any questions so far?
Well, none so far.
Okay. So the point of doing this is that now I get some optimization that is more easier to handle. So this sort of optimization where you optimize over some distribution, they have a long history in optimization theory, and they are known as a distributional optimization. And the idea is that if you have some optimization over distribution, you can do some Monte-Carlo sampling and optimize over the samples. So before I go on with the Monte-Carlo sampling, I just want to mention that both in supervised model and unsupervised model, I actually can go and simplify these loss functions, and I get a very nice, a more compressed form of optimization where you have some optimization over distribution here. And these optimization are known as the kernel target alignment in machine learning. So Now I have two optimization here, one for supervised model and another one for unsupervised model. But as you can see, they both look like the same. They are kind of similar to each other. So for the rest of the talk, I only focus on the unsupervised model because whatever I say here can also be applied to the supervised model. So the first step here is I take this optimization kernel target alignment. I write it as a risk minimization problem. So from this optimization to this optimization, I basically didn't do anything. I just rewrote it in a different form. That's what I did. And the next step, as I said, is to do some Monte-Carlo sample average approximation. So instead of optimizing the distribution, I just optimize over a bunch of samples from this distribution. And here, I'm assuming that the space of distribution that I'm searching for is a distribution ball. So you have some set of distribution that satisfies some divergence property. And for these samples, I can define an empirical measure. So you can think about this empirical measure as an approximation of the true measure that I'm trying to optimize. And after that, we apply some stochastic gradient descent to these samples from the distribution. So I initially, I have a bunch of samples from an initial distribution. And then I do some sampling from the data. So these are my training data. I have some training data that I can use. And then I apply a stochastic gradient descent to these samples to update them. And after I updated the samples, I can approximate the kernel. So this equation here is basically an approximation to the integral representation of Rahimian rect that I showed you previously. So we had the integral representation here. I am taking a bunch of samples, optimizing over them, and then I can approximate the kernel using the sum. So this is basically a Monte-Carlo approximation of the integral. Now, I want to show you first some simulations. So these samples from the distribution that I talked about, you can consider them as some sort of particles that are moving in the space. And you can assume that SGD, stochastic gradient descent, as some sort of law that moves these particles around. And you can plot the histogram of these particles. So suppose I initially choose these particles from a uniform distribution. So, and this is the histogram. And as you can see, after a couple of iterations of SGD, these particles take a very interesting shape, which looks like a Gaussian distribution. So there are interesting things going on here. The first question is, what happens if I choose a large number of particles? Do I get a distribution? And it seems from these plots that it is true. The conjecture is true that if you choose a large number of particles, you are finding a distribution. And this distribution is the object that I'm interested in this talk. So I want to first show a theorem that says that the Monte-Carlo approximations that I've done so far is consistent. It means that if I choose infinitely many particles, then the optimization problems that I had is not gonna change. So the solutions that I get from the optimization using Monte-Carlo sampling is similar to the solution of the distributional optimization. So in this theorem, I have two optimization. One is with respect of the distribution that I had, and another one is with respect of the samples. So here I'm optimizing the empirical measure with respect of the samples. And the theorem says that if you choose a large number of samples, from the distribution, and if you have enough training data, then the approximations that I've done to solve the distributional optimization is consistent. So here I have a bunch of parameters, and capital N is the number of samples that I take from the distribution of the kernel. Small n is the number of sample training data samples. So I have a bunch of training data. Remember that this kernel learning is supervised, so I have a bunch of training data. And there is a parameter alpha, which is about the approximation that I made to write the optimization as a risk minimization. So when all of these parameters goes to infinity, these two objective functions correspond to each other. So this theorem is basically an application of law of large number, if you will. Now, another interesting thing that I talked previously is that if I plot the histograms at a fixed iteration of SGD, so let's assume that I only run the SGD for a couple of iterations and I fix that, and I increase the number of samples or particles. So as you can see, you converge to some sort of distribution, and the goal is to characterize this distribution. So these are the particles from SGD. I can compute the empirical measure of these particles. And from the plots, I can see that when the number of particles goes to infinity, then this empirical measure converges to some limiting measure. And the question is, can I characterize this limiting measure? It turns out that this limiting measure it can be characterized using some PDE equation. So this PDE equation comes from statistical physics, where people in statistical physics have studied these systems of many particles for a long time. And the PDE that describes the evolution of the empirical measure is called McKim loss of mean field PDE. And it has a very complicated form, but it turns out that it can be solved numerically, and you can go and compute this, the solution of this PDE. And the solution of this PDE gives you the precise form of the empirical measure when the number of particles is infinite. Another interesting thing that we can conclude from this PDE is that these PDEs actually can be viewed as some sort of gradient flow of an energy function. So it turns out that this PDE is a gradient flow on some Wasserstein manifold. And the nice thing about it is that what this theorem actually is saying is that if I have enough number of samples, this particle SGD is actually minimizing the distribution that I was interested in. So remember, I had some distributional optimization, but I didn't optimize over the distribution, I optimized over the samples. And I use an algorithm to optimize the samples. What this theorem is saying is that if I have enough number of samples, this SGD algorithm is actually minimizes the objective function over the distribution. So in a sense, what this says is that the algorithm that I used to optimize the samples is actually consistent. So I had two sort of consistency result. The first one was to show that when the number of samples is large enough, my optimization problem doesn't change. The second consistency result is about what happens to the algorithm. And this theorem says that if you have enough samples, the algorithm that we use to optimize the samples is also consistent. So I want to show some simulations. First, I show simulation on synthetic data set. So, for the synthetic data set, for the synthetic experiments, I'm considering a hypothesis testing problem. So here I have two distributions. Both of them are Gaussian, multivariate Gaussian distributions. And the variance of this Gaussian distribution has a parameter lambda. And this parameter changes from 0 to 1. And for lambda equal to 0, I have similar distribution to a standard multivariate Gaussian distribution. As lambda approaches to 1, you have two separate distributions. And here in figure 5, I'm showing you the samples from these distributions. As you can see, for lambda equal to 0.9, you have a situation where the distribution, the samples of the distribution are separate from each other. It can be distinguished from each other. For lambda 0.1, you have samples that are kind of mixed, and it's more difficult to distinguish if one samples come from distribution 1 or distribution 2. So in a sense, lambda determines the difficulty of hypothesis testing. So here, the hypothesis is if I have a bunch of observation from distribution P null, and I have a bunch of these samples from distribution P1, based on this observation, can I determine if these distributions are equal or different? So my null hypothesis is lambda equal to 0. My alternative hypothesis is that lambda is bigger than 0. One way to do this hypothesis testing problem is to use the kernel to design a test statistics. So remember, MMD is a notion of divergence between two distributions, which uses a kernel. And if I have these observations from each distribution, I can actually compute some sort of divergence between their empirical measure. And if this divergence is smaller than some threshold, then I announce the null hypothesis. If it's bigger than some threshold, then I declare the alternative hypothesis. And if I use a kernel without trying to optimize it, I get some curves, some performance here in figure C. So the ideal case is I would like to increase threshold, and I would like my hypothesis testing still gives me accurate result. So it means that I would like to shift this curve to the right-hand side. And as you can see, if I don't optimize my kernel, I get this result for different lambdas. In figure A, I apply my kernel learning, and as you can see, I have increased the threshold. So the performance of the hypothesis testing in figure A is much better than figure C. In figure B, I'm also trying to optimize the kernel, but the way that I do it is using an autoencoder. Autoencoder is basically performs some dimensionality reduction, but it doesn't give the good result as my kernel learning approach in figure A. So this was the result on synthetic data set. Let's go to the benchmark data set. So here I'm showing you the result from CIFAR10 and MNEST data set. In figure B and figure C, I use MMD GANs, but I optimize the kernel using cross-validation. So what it means is that I have a validation set, and I can tune the parameter of the kernel and see its performance on the validation data set. In figure A, I'm showing you the result using the kernel optimization approach that I discussed in this paper.
I'm sorry to interrupt you, Doctor. I believe we have a question.
Yes.
Let me give the voice to the person who has a question. Well, there seems to be a voice problem with our attendee. So we are sorry for the interruption. Please carry on until we get the question in a written form.
Sure. Right. Yeah, so this is the performance of kernel learning for generative modeling. And as I mentioned here, I'm getting my result. So this is images produced by MMD GANs. And in this case, in plot A, I'm using the kernel optimization approach. In plot B and C, I'm tuning the parameter of a Gaussian kernel over some validation data sets. And visually they look similar, but what this figure doesn't show is the amount of time you need to optimize the kernel. Clearly, if you use a validation data set, if you use a cross-validation technique, it takes much more time to optimize the kernel. But in figure A, you can optimize the kernel very quickly. And I will show you some quantitative result with regard to the runtime of each method. I have more figures from different benchmark data sets. So I have Celeb A and LSU bedroom data set. And again, visually, it's very hard to distinguish between the results using cross-validation and kernel learning approach that I mentioned. There are also some quantitative performance measures for GANs that determines how if these images that I showed you is good or not. And these are inception score and fresh FID score. So inception score, when it's higher, it shows better result. FID score, when it's lower, it means that the results are visually better. And as you can see, our algorithm produces better result compared to MMD GAN with Gaussian, mixture Gaussian, when you fine tune their bandwidths. So even though you cannot probably see it from the figures, the quantitative results shows that the performance of our approach is better. We also applied our kernel learning for some classification tasks. So there are a bunch of benchmark data sets that people use to validate their algorithm. And these are called buzz, online use, popularity, adult, and seizure. These are some real world data sets which we use for classification. And here in this plus, the blue curve shows the training and test error of kernel SVMs, kernel support vector machine. And we use different kernel optimization approach. And as you can see, the blue curve shows a better result. This is our method. The red and green ones are two other alternative methods to optimize the kernel. The red one is a method called importance sampling. It's a work by Janducci and Aman Sinha in NIPS 2007. And the result, as you can see, the test and training accuracy from their method is not as good as our method. But the catch here is that using our method, you need to, the runtime of our method is higher than their method. So you can get better result, but the cost is higher runtime. In this plot, I'm showing you the TSNE of those classification examples that I showed you. So in figure A, it's a TSNE plot of our method. Figure B is the TSNE plot of importance sampling of Janducci and Aman Sinha work. And this is a TSNE plot from a kernel that is not optimized. And as you can see clearly from figure A and B, it's much easier to discriminate between the blue and yellow regions. But if you don't optimize the kernel, as you can see in figure C, it's very difficult to get a good accuracy. So I want to quickly go through a couple of more slides. These are more, has some more mathematical side. So as I mentioned, you can consider the particles or the samples from the distribution as some sort of particles that move around in the space. And it turns out that these particles, as their number increases, they satisfy some independence property. And this independence property has a different name in statistical physics called propagation of chaos, which is kind of a mouthful name, but I will quickly explain what this property means. So the first definition that I need is the notion of exchangeability. So a probability measure is exchangeable if we apply some permutation, if it's invariant under some permutation. So if I have a probability measure and I have a bunch of permutation of indices, exchangeability means that the value of this probability measure is invariant under this permutation. The next definition is chaoticity. Chaoticity means that if I have a measure on the product space and I apply a bunch of test function, so if I integrate this test function with respect of this product probability measure, when the number of the dimension of this product measure goes to infinity, I can separate this measure. So the measures become independent over each coordinate. And for Markov process, we can also define the notion of propagation of chaos. So for a Markov process, if I have an initial distribution, I can determine the distribution at a later time using this integral. This kernel is a kernel of the Markov process. So if I take a distribution and fold product of a distribution and I apply this kernel, I can get its value at some later time. And propagation of chaos means that if I have a distribution, initial distribution that is chaotic, then if I apply this kernel, the later distribution at the subsequent time is also chaotic. And this is the definition of propagation of chaos. And the theorem that I have here, and we proved it in our paper, is that if the initial distribution of these particles is exchangeable, which means that the initial distribution is invariant under some permutation, then the distribution, the empirical measure of this particle at a later time is also chaotic. To give you a bigger picture, what this theorem says is that if the number of particles, if the number of samples is large enough, then their dynamics become decoupled. So it means that they become, they move around independently from each other. So you can, if I go back to my optimization theory again, here I have some dynamics for the particles, but as you can see, the movement of each particle is dependent on the other particles. So I need to know the location of other particles to determine what is going to be the location of a particular particle at the next time. But as the number of particles increases, this chaoticity and propagation of chaos tells me that the dynamics decouples. And this is a nice property that people also have studied in the statistical physics. So I want to conclude my talk. This talk was about different models of machine learning based on kernels. And I talked about some issues with these kernel models. They typically facilitate the training, but they also have their own model selection problem. And it is, in this talk, I gave you a way to optimize these kernels and resolve the kernel model selection problem. And I also provided some properties of this algorithm and some theoretical and empirical results on benchmark datasets. Okay, I can take questions if there is any questions here.
Well, there seems to be no questions right now. Thank you for your time, Doctor.
Thank you. Thank you for listening. I appreciate it.
I appreciate the time you've given us.
Bye-bye.
Goodbye.